Welcome back, everyone. The global shipping industry is facing an unavoidable transformation as the demand for clean energy grows and the regulatory timeline for practical solutions tightens. Cargo ships burn enormous quantities of heavy bunker fuel that produces pollution far in excess of most land-based transportation systems. And this pressure has created an opening for nuclear propulsion to re-enter the conversation in a new and safer form. Thorium-fueled molten salt reactors have emerged as one of the most realistic technologies capable of powering the next generation of deep ocean cargo vessels by the late 2020s, with several engineering groups projecting test deployments before 2026. For the first time in decades, the energy profile of global shipping might shift from petroleum to a compact and extremely high energy density system that can operate for years without refueling. Thorium attraction begins with the basic physics of its fuel cycle. Thorium itself is not fissile, but when it absorbs a neutron, it converts into uranium that is fissile inside a molten salt environment. The liquid fuel mix removes the coolant limitations that constrain traditional reactor designs and creates a stable thermal envelope suitable for the constant power demands of large marine engines. A cargo ship powered by a thorium molten salt reactor could run continuously at sea for years. And this long endurance immediately solves the logistical challenge of carrying enough fuel for voyages that cross the entire planet. The process eliminates sulfur emissions, since there is no fuel oil involved, and reduces the total emissions to nearly zero for the vessel itself. The fundamental engineering advantage of molten salt reactors is the way the liquid fuel and coolant combine into a single chemically stable mixture. Rather than relying on pressurized water systems that must contain extreme pressures, the molten salt operates at atmospheric or near-atmospheric conditions. This eliminates the risk of rapid pressure release events and allows the entire reactor vessel to remain compact and modular. For a cargo ship, this translates into far simpler maintenance, lower mechanical stress on the hull, and fewer high-pressure systems that could complicate regulatory approval. A compact reactor core could sit in a shielded compartment near the center of the vessel, with additional layers of structural protection that do not require major redesign of the entire ship class. The most important safety feature of a thorium-based molten salt reactor is the freeze plug mechanism. A drain tank sits below the reactor core and is held in place by a frozen salt plug maintained by active cooling. If power to the vessel were lost, or if temperatures rose beyond a safe threshold, the plug melts naturally, and the liquid fuel drains into a geometry that cannot sustain a chain reaction. This passive safety response requires no human action, no electronic control, and no mechanical valves. For maritime operations, this is critical because conditions at sea do not always allow quick manual intervention. A reactor that enters a safe configuration entirely on its own offers a major advantage for international regulators evaluating nuclear propulsion in commercial vessels. A thorium molten salt reactor for cargo ships would also provide an enormous amount of thermal energy that can be converted into electricity using a closed-cycle turbine system. Unlike naval reactors that often use steam directly, commercial designs being tested for civilian maritime use favor high-efficiency gas-based turbine systems that can accept heat from the molten salt without exposing the working fluid to radiation. This arrangement protects the rest of the ship from contamination risk and isolates the reactor as a self-contained power source. The electrical output can then feed large-scale electric propulsion motors that drive the ship's propellers. These motors are exceptionally reliable, require little maintenance, and allow precise thrust control during docking operations or tight maneuvers. By 2026, several research groups in Europe, Japan, and the United States expect to have demonstration units ready for industrial evaluation. The goal is not to put a full-scale reactor on an ocean-going vessel immediately, but to finalize the materials science and thermal control systems needed for maritime certification. One of the most important steps involves corrosion testing, because molten salt interacts with metal containment structures differently than water-cooled reactors. High nickel alloys and advanced weld treatments are being developed to ensure that the reactor vessel retains structural integrity during extended voyages. Once these material standards are locked in, shipyards can begin designing hulls that integrate the reactor compartment as a drop-in module. A cargo ship equipped with a thorium molten salt reactor could travel around the planet many times without refueling, which completely changes the economics of global freight. Ports would not need to store heavy fuel oil, ships would not need to bunker in specific locations, and transit schedules would become more predictable. Weather disruptions could be countered by simply adjusting course without worrying about additional fuel consumption. This endurance also improves safety, since the vessel can maintain full power to outrun storms or avoid hazards without the fuel restrictions that plague conventional fleets. Over decades of operation, the cost savings from eliminating fuel purchases may exceed the cost of the reactor itself. There are still regulatory barriers to address, especially concerning how international waters treat nuclear-powered civilian ships. However, the use of thorium and molten salt designs changes the conversation significantly. The reactor cannot melt down in the traditional sense, has no high-pressure water system to rupture, and produces far less long-lived waste compared to traditional uranium fuel cycles. In fact, most thorium waste decays to safe levels much more quickly than outputs from pressurized water reactors. These advantages give regulators a path to approve limited test fleets under controlled conditions. And several maritime authorities have already begun drafting guidelines that evaluate new reactor types on their passive safety characteristics rather than older assumptions from mid-20th century designs. Another major benefit of thorium reactors at sea is the potential for onboard industrial processes. The intense and constant thermal output can supply high-grade heat for synthetic fuel production, desalination, refrigeration, and onboard hydrogen generation. Some cargo ship operators are exploring hybrid operations, where the vessel produces hydrogen for portside power during unloading periods. This would turn each vessel into a floating energy platform that supports coastal energy needs each time it docks. Such capabilities are difficult to achieve with conventional ship engines, but become practical when a ship carries a compact reactor capable of constant multi-megawatt heat production. If the engineering, safety, and regulatory challenges are solved, thorium molten salt reactors could redefine maritime transport by the late 2020s and early 2030s. The combination of endurance, safety, and fuel availability creates a compelling case that shipping companies cannot ignore as global pressures for cleaner energy intensify. The next 4 years will be decisive as test reactors complete qualification and shipyards begin incorporating modular reactor compartments into prototype hulls. Whether the first commercial vessel launches in 2026 or slightly later, the momentum behind thorium at sea is real and growing. The world of global shipping may soon be powered by an entirely new class of compact and inherently stable reactors that operate far from shore and deliver reliable power to vessels that tie the world economy together. One of the main reasons driving the interest in thorium reactors at sea is the shifting economics of global trade. Shipping companies have struggled with unpredictable fuel prices that can swing wildly in just a few months, making it difficult to plan for the long term. But a ship powered by a thorium molten salt reactor would eliminate this kind of instability, locking in predictable operating costs for decades. Investors in maritime infrastructure see this stability as a hedge against all the uncertainty in the global energy market. And, interestingly, it opens up the possibility of completely new trade routes that aren't limited by where fuel is available. With steady power at a stable cost, freight operators could start using more direct routes across remote parts of the ocean. That would cut down transit times and enable new logistics models that weren't practical before, given the old fuel constraints. Thorium-powered cargo ships will also have a big impact on how ports are designed around the world. Traditional port infrastructure is built to handle things like fuel storage, pollution management, and heavy engine maintenance. But a vessel with a reactor on board doesn't need any of that. Instead, it brings new requirements. Upgraded security, licensing offices, and radiation monitoring stations to check the reactor's status when the ship arrives. Port authorities in places like Europe and Japan are already looking into what changes would be needed to welcome a fleet of nuclear-capable cargo ships. These changes aren't as major as some people might think, since the reactor itself stays sealed and is totally inaccessible during normal operations. Still, ports do need to show responsible oversight, and once these systems are in place, they'll become global standards, similar to how containerization transformed ports back in the late 20th century. Engineering teams are also exploring how thorium reactors can integrate with emerging electric propulsion systems. Large-scale marine motors are already being developed for hybrid and fully electric vessels, and the constant output of a molten salt reactor fits naturally with this approach. Instead of using variable-speed diesel engines that constantly ramp up and down, a reactor can produce a steady flow of electrical power into a bank of high-capacity inverters. These inverters then supply propulsion motors that adjust their speed instantly in response to navigation requirements. This arrangement reduces mechanical stress throughout the propulsion chain and simplifies service schedules. It also offers a level of maneuvering precision that conventional ships cannot match, which is especially valuable when navigating crowded ports or narrow channels. Another emerging advantage is the opportunity to use thorium maritime reactors as test beds for future terrestrial systems. Many of the engineering challenges associated with ocean-going reactors, such as constant vibration, rapid temperature swings, and corrosive environments, mirror the conditions required for ruggedized land-based reactors intended for remote or industrial regions. If maritime prototypes demonstrate reliable performance across long voyages, the same core designs could be adapted for mining operations, polar research facilities, or isolated manufacturing environments. This cross-compatibility strengthens the economic case for development because research investments serve both marine and terrestrial reactor markets. Several engineering groups are already outlining dual-use platforms that could streamline certification for both maritime and land-based operation. The final factor accelerating interest in thorium-powered shipping is the possibility of nearly autonomous reactor management. Molten salt reactors operate at stable pressures and rely on passive safety behavior that does not require constant control room adjustments. Advanced sensor arrays and predictive analytics can monitor salt temperature, neutron flux, and pump performance in real time, while alerting crew only when thresholds are exceeded. This reduces crew workload and allows the vessel to focus on navigation rather than energy management. Over the coming decade, these systems may evolve into partially automated reactor modules that require minimal intervention while remaining fully transparent to regulators. The potential combination of endurance, safety, automation, and high energy density explains why thorium reactors at sea are drawing serious attention as a practical power source for the next generation of international cargo fleets. Thank you very much for watching. Please like and subscribe.